say some minimum value is black and some maximum value is white. Oh, I didn't say it has to be 0. It has to be some minimum. So I could make like minus 128 be black and plus 127 be white, or minus 20, and I could make 0 be gray. So what you're seeing here on the right is what's referred to as a gradient image, where gray is 0, white means positive, black means negative. This is sort of mess you up in doing some of the problem sets, etc. But remember that the display of an image is just for convenience for me and you when it's a mathematical function like this. Here's another example, partial derivative. So here we have another animal that tends to have stripes, although I would not get as close to this one. So first question, which one's the x and which one's the y? Well, let's see. Again, we have some vertical stripes here, and we see them right there really strongly. So that changes as you go to the x. They don't show up over here so much, but here we have horizontal stripes, all right, that show up nicely. You probably figured out by now that on the left-hand side, we have the partial with respect to x. On the right-hand side, the partial with respect to y. And in fact, if you take a look at this, you'll see that, and I'm going to make sure I put these in the right way, is that when I get to this edge right there, which is this edge right there, that as it gets brighter, that value goes high. So the filter that I'm using here is this -1 + 1 correlation filter. I take the value to my right, subtract off the one from my left, and that's the value. And now correlation versus convolution matters, because if I swapped it around, things would be different. On the y side, it's also going to be +1 or -1, but I write it like this. And the reason that I do that is one of these is the filter that you would use for computing the y gradient. But whether it's the one on the left or the one on the right will depend if whether in your universe you make y go up positively or you make it go down positively. And that's a choice that you get to make. You can put the origin of your image in the top left-hand corner, like computer scientists tend to think about them, or in the bottom left-hand corner, like mathematicians for thousands of years have done that. Only computer scientists would screw with that, but we did. So you'll probably have to figure out which way y is in your world and then apply the right filter. By the way, I can take the magnitude of this, that is just take the sum of the squares and take the square root, and I would end up with a picture that looks like that. And that should start to give you a hint as to where we're headed, because that looks an awful lot like an edge image. So those are our discrete gradients, but now we said we wanted an operator, right? We want a mask or a kernel that can implement these gradients. So here's an example of an operator, h, and I'm going to use 3 rows, and I'll tell you why in just a minute. For now, we only have these 2 columns. And so the question is this a good operator?
No.
No, it's not a good operator. Why is it not a good operator? Well, there's a couple of reasons. One of which is there is no middle pixel. So it's hard for me to say that this pixel's value, because the question is, what's special about the right? It should be, I could also be able to go to the left. So if I wanted to do that, what might I do? Well, I might do an operation that looks like that. I'm going to go to the right here and the left there. Now you might ask yourself, why is it a +1/2 and -1/2?
Why is it?
No, ask yourself. Don't ask me. Well, okay, here's why. It's the average of the right derivative and the left derivative. And what I mean by that is the right derivative would be a +1 here and a -1 there. Okay? The left derivative would be a +1 here and a -1 there. If I wanted to average them, I would add them and divide by 2. So I add them, I get -1, 0, 1. And then when I divide by 2, I get -1/2 and +1/2 with a 0 in the middle. So that's why this thing that goes +1/2 to the right, -1/2 to the left is the average of the left and right derivatives. Get it? Cool. People have been doing derivatives and edges for a very long time. The most classic one is referred to as a Sobel operator, named after Leonard. I have no idea. It's named after some guy named Sobel. And the Sobel operator looks just like what I was showing you, but instead of 1/2 and -1/2, it's got this weird thing where it's doing these eighths, and you can see that it does it not only +2, -2, which you would then divide by 4, and you'd get the same value, but it also does a +1, -1 on the row above me, and a +1, -1 on the row below me. And the idea here is that if I'm taking a derivative, remember how we said before we assume that our images are sort of locally smooth, that is, they change similarly. So the idea here is that if I'm going to compute a derivative at a pixel, I won't look just left, right at me, but I'll also look nearby me. And then to normalize this thing, you have to divide it by 8. By the way, having just almost finished teaching the course here on campus, we had a problem set where people were having a heck of a time that they hadn't had a problem with before. Turned out somebody had discovered that MATLAB has a built-in function called imGradientXY. And they said, could we use that function to compute a gradient? Since it was for a part of a problem set that was more advanced and they had already done gradients, I said, sure. And all of a sudden people are having all sorts of problems. And the reason was, if you look up imGradient, it tells you that it applies the Sobel operator by default. Well, here's the Sobel operator, looks great, but you know what? It doesn't divide by 8. So all their gradients were scaled by a factor of 8. And it totally screwed up the entire class. 100 people got screwed up because of this. So now we tell them you can use imGradient, but you better divide by 8. By the way, the y one is here as well. And in this case, y is positive going up. Remember, it could go in either direction. All right, so the Sobel gradient would just be made up of the application of this Sx and Sy to get you these values. And the magnitude is just the square root of the sum of the squares. I should have said that Gx is the application of Sx, Gy is the application of Sy. So the magnitude is just what we did before. And here's the arctan2, the atan2 that we were talking about in order to get the gradient. So here's an ancient example. It's so ancient I know because that's X Windows, so that even predates when most of you were born. And here you have a picture on the left that's an image. Here's a gradient magnitude, so you just apply the Sobel operator, take the sum of the squares, square root of. And then, by the way, you could just threshold it. And you'll notice two things. One, it's not an awful edge image. And two, it's not a great edge image. All right? So we're like partway there. Right? We're partly towards getting that done. There are lots of well-known edge operators. There's the Sobel, and then Pruitt and Roberts, which you can see does these different kinds of ways. MATLAB basically understands all of these. And in fact, in MATLAB, there's this cool little function now called fspecial, which will make filters for you, depending upon the name. That's in, might be in the IMFilter toolbox only or basic MATLAB. But the idea is that you can give it Gaussian, you can give it Sobel. And if you give it Sobel, what it'll do is it'll reply back this operator, okay? And in this case, by the way, turn everything into doubles in MATLAB. If I apply that to some image, all right, so here's the double of my image, I apply the filter, and then I display it, and I use a gray color map, and you can see it gives me that gradient image, okay? And that's the Y gradient only. It also gives you back the X gradient. Quick quiz. It is better to compute gradients using convolution, since that's the right way to model filtering so you don't get flipped results. B, correlation, because it's easier to know which way is which way the derivatives are being computed. C, it doesn't really matter. Or D, neither, since I can just write a for loop and it'll compute the derivative. Well, this is a tough one. The answer is either B or C. Look, as long as you keep track of what's going on, it doesn't matter. You can do whatever you want, in which case it would be C. Remember before I showed you those correlation operators, I said I'm doing correlation because I want to know which way is the right way, to the right versus to the left. So I think when you're doing filtering for gradients, doing correlation probably works better for you. And by the way, so in the old days, we used to have to either call correlation or convolution explicitly in MATLAB. Now we tend to use IMFilter, as we've talked about before. IMFilter, by default, does correlation. So if you want convolution, make sure you tell it. All right? So you just have to keep track of that.
Let's take a closer look at gradient directions, especially how they are computed and represented. How about we use an image that has clearly defined edges at distinct angles, like this. Note that we convert the image to double type after reading and scale it down to a 0 to 1 range. This makes it easier to track down numerical issues that may crop up. It also makes it convenient to display because IMShow assumes a 0 to 1 range for double images. MATLAB and Octave have a direct way of computing image gradients. imGradient_xy is the function. It returns a pair of matrices, the first one being the gradient in x direction and the second one in the y direction. I'm pretty sure the default filter used is Sobel, but you can also mention it explicitly. Let's try to visualize the gradient images. But note that imGradient_xy does not normalize the gradient images. Therefore, we must scale them to the appropriate range. Now, why do we need to add 4 and divide by 8? To understand this, let us consider the Sobel operator, which looks like this. Now, what happens when this filter interacts with an image or an image region that is black on the left-hand side and white on the right? All these negative coefficients, they get multiplied by 0 and cancel out, whereas these positive coefficients get multiplied by 1 and sum to 4. So the total response of the filter at that position would be 4. Similarly, an image region which has white on the left-hand side and black on the right-hand side would result in -4. So our gradient values are in the range -4 to +4. If we add 4 to each of these values, the range shifts to 0 to 8. Hence, dividing by 8 gives us a 0-1 range. Enough with the math. Now what does this look like? As expected, in the x gradient image, you see the vertical edges show up. Similarly, you can view the y gradient. This time, the horizontal edges show up more clearly. Note that on your local machines, you should be able to simply pass in the expected range and let IamShow do the scaling. If you leave out the limit values and pass in an empty vector, then IamShow will scale the image based on the actual minimum and maximum values found in the image. This can give slightly different results. For instance, say the minimum magnitude found was -3.5. This behavior is similar to what ImageSC does, although that has other options for setting the color map, etc. Okay, now that we have the x and y gradients, we are interested in computing the overall gradient magnitude and direction. Fortunately, there is a function to do this in one step. The magnitude returned is the Euclidean norm of the gradient in x and y directions. As we saw earlier, each of those could have an absolute value of 4. So the total magnitude values can go from 0 up to 4 times √2. And that's what we use to scale it by. This is what the gradient magnitude looks like. The edge pixels are not super bright, which kind of indicates that the edges were not as sharp. But that's okay, the edges are still distinctly visible. Remember that the gradient direction is an angle computed as the tan inverse of y by x gradient values. The result is returned in degrees ranging from -180 to +180, where 0 degree corresponds with the positive x-axis, and increasing angle rotates counterclockwise. The right edge has gradient pointing at 0 degrees. Gradient values in the plane areas of the image are undefined. Since they have to be set to some number, they're also 0, which is why you can't see the gradient values along the right edge. As I mentioned, angles go counterclockwise. So this is 45 degrees, 90, 135. Interestingly, gradient pointing to the left is at 180 degrees, which is the same as -180. And here are the other angles, for good measure. Now I want you to write a function that finds pixels with desired gradient direction. The function should be called select_gdir. The first couple of arguments are the gradient magnitude and direction images. The third is the minimum magnitude value we want to consider. This is to filter out noisy pixels that can have random gradient directions but usually low magnitude. The last two arguments specify the desired gradient range, low to high. For instance, here we want to look at gradients in the 45-degree angle with a ±15 margin. Note that you need to return a binary image that can be displayed with IamShow. Here's some code to get you started. Okay, the solution is actually a one-liner. Firstly, we know that we want pixels that have at least the minimum magnitude specified. We can use relational operators to directly compare matrices with scalar values. This is essentially a thresholding operation. Next, we use a pair of comparisons to say that GDIR should be between angle low and angle high.